Um, we have our exam on Monday. You have a copy of the old exam, exam number two from a previous semester. Um, but I just want to go ahead and recount like what we've covered this week and what to sort of anticipate for the upcoming exam. The first thing that I want to mention is that since all of the exams are kind of cumulative, um, I mentioned that with the grading scheme, like exam two's grade can be replaced by exam one. Um, if everyone, I hope everyone remembers that, just so we don't have to rehash that at this moment. What you should expect for your exam on Monday is about 30 to 35% of the questions will be similar to exam one. And so that means about 65 to 70% of the exam is all of this stuff that we've covered this week. So I made a correction to the, or not a correction, but I fixed a mistake of mine, and that was that I made it so you can see your answers from exam number one. So I would definitely use those questions and go back and say like, okay, why is this right? Why is this wrong? So you should be able to see the correct answers, and I believe you'll see what you answered. Um, so those are just some things that you should probably anticipate and maybe plan for. The way that I think that, you know, regardless of how like I feel like it's almost a philosophical discussion, but there's always going to be some strategy in how you prepare for an exam. Like, any exam is going to be, oh yeah, it's all content. Yeah, absolutely. But there's a strategy for how you approach that content. So my recommendation for this upcoming exam on Monday is I would go through exam one, and I personally would focus on the questions that I got right, just to sort of cement that and say, and ask myself that critical question of, did I get this right because I knew it? Or did I get this right because I narrowed it down to two and I flipped a coin? Um, and then there's also the possibility that it's like, I got it right because I misread the answer option. Um, so I think that it's important to be like reflective on questions and say, why did I get this right? Do I know this? Yes, I'm going to move forward with my life. Do I not know this? No, I'm going to shore up that information now. So that's one thing that I would recommend for the upcoming exam on Monday. Now, do not expect that a question is just going to be reworded and it's going to be flipped from, an affirmative to a negative question. Instead, think like, okay, how could I ask this same, like, what's the concept that's being asked behind this question? And how could that question be asked slightly differently? That's what I would recommend because I'll use old exam questions, but I'm not just going to, shuffle the answer options around, and I'm not just going to say, like, well, the answer was one and now it's negative one. Done. I recommend like looking at the concept underlying the question. Then for this upcoming this week's content, um, this week is about types of interactions. It's about bonds. It's about ionization. And then, if you remember, yesterday's lecture was pretty short, and that was by design. I sincerely want you to practice being able to quickly calculate a charge. Um, I want you to be able to, you know, visualize a structure at a given pH. And that's for single amino acids as well as peptides. Now, what I want to share with y'all real quick is I'm going to switch is this resource right here. I did a Google search, or actually, I got a new computer not too long ago, so now my default browser is Yahoo. That's how they have to do it. They have to like get you preloaded software where, oh yeah, it's Yahoo. That's the browser that I wanted to use. Nobody ever really says that, I don't think. Um, so peptide draw, Google it or Yahoo it. And there's two different links. There's this pepdraw.com, but then there's also this URL found or hosted by Tulane University. I'm going to go to both of them. They're very similar, but there's one thing that's a little bit different between the two. The one that's hosted on pepdraw.com, what this is, or what's really cool about this tool is you can type in, anything really. You can type in a 15 amino acid long sequence, and let's go ahead and QWARDEVCSILE. There we go. That's a polypeptide right there. All of those, and I'm always nervous about whatever I'm typing that I'm actually accidentally going to type a swear word or something. I don't think that Quardivicil is problematic, but what this tool allows you to do is quickly draw the peptide. So here's the skeletal structure of this peptide, starting from the N termini on the left-hand side all the way to the C termini on the right-hand side. Typically, whenever I draw a structure, I'm going to draw the structure where I show every single atom. A carbon is a C as far as I draw, because I'm not really an organic chemist. If you're comfortable with the skeletal structure, that gives you a heads up. In addition to that, what this tool gives you is it gives you a calculation of the isoelectric point, the PI. Then it also gives you a net charge calculation. Now, a net charge, that's only going to be calculated based on the solution that it's in. And the reason that I like this pep draw more than the one that's hosted at Tulane is because here you can dictate the pH. So if I wanted to say, I'm going to change this from, this is displaying this peptide at a pH of 7. Now I want to change it to do 1.5. I'm going to adjust the pH of this down to 1.5. I'm going to redraw this peptide. And it really looks very similar. However, there are some differences, and there are important differences to recognize. For starters, we've got R groups that are protonated. We have carboxylic acid R groups. Those are all examples. And here's our C termini that's protonated. And then here's one that I really want to highlight right here. This most recent one that I drew a box around. In fact, to emphasize that, I'm going to draw a double box. Well, let's see. That would be a beta carbon, a gamma carbon, and then a functional group that has a carbonyl carbon and NH2. Man, that's a lot like glutamine. And that is the glutamine R group. Now, one thing that I want you to recognize about this is that glutamine R group does not have a positive charge. Why is that? Well, because glutamine is not a polar positive residue. It's a polar uncharged residue. So even at a pH of 1 or 1.5, it's not going to have a charge. Now, all of the groups that I've highlighted, what I want to do is I want to bump the pH up to, let's go with 13.6, an absurdly high pH. Kind of take a mental snapshot of all the groups that I highlighted, and boom. First and foremost, that glutamine R group didn't change. The ionization state of that did not change. That's a polar uncharged residue. But then all of these other groups, they went from either positive to neutral or neutral to negative as I jump my pH up. And some you'll see, like there's this hydroxide group that I have highlighted, or with a box around it, that again, I'm going to pick another, I'll draw another box around that. This group right here did not change its ionization state. That's a serine residue. So I think that this is helpful because, when you're drawing a peptide, you can visualize an amino acid. At the same time, you can type in a single letter. I'm going to clear all my drawings. Eraser, clear drawings. Should be a clear. All drawings. Okay, so there's alanine at a pH of 13.6. What's the charge on alanine at 13.6? -1. How about let's go to alanine at a pH of 0.5. Oh, the charge is +1. So from a pH of 0.5 to 13.9, this molecule goes from +1 to -1. So the only downside of this is that it doesn't have your pKa values. Maybe you could get the pKa values here. I've actually never clicked help because I don't need help. Not really, because I always just like to type in funny words and then draw the peptide. Well, let's see. Where you at? Peptide draw, pepdraw.com. Let's see what Tulane has to say for help. Okay. Let's see. Yeah, it doesn't give us no dice on the pKa values. Hydrophobic interactions. Um, that is one downside of this. It doesn't have pKa values. I wouldn't expect them to dramatically differ, but nevertheless, the the last thing that I want to mention with respect to this is these right here. Those are modifications of amino acids, or they're less common amino acids. They are proteinogenic amino acids, so they have single letter codes. And as you look at them, when it comes to typing in a peptide and typing in a cool peptide, basically what I'm saying is a cool word, you can see you get a U there. So is U assigned to one of our 20 proteinogenic amino acids? No. Is it assigned to a proteinogenic amino acid that is a less common amino acid? Yes, it is. Uh, but that's like an exception to the exception. So for all intents and purposes, as far as we're concerned, U is not used as one of our 20 proteinogenic amino acids. But as you can see, whenever you get the letter U, now all of a sudden your ability to type in swear words and draw peptides of swear words, oh, the world is your oyster. And also pyrrole lysine, that PYR, that gives you the letter O. So now you can type in oyster. Um, at any rate, I wanted to share that with you because if you're like, I need more practice with this, here you go. ASEF, practice. Let's draw it at a pH 1. Practice. What about 1.5? Oh, it doesn't change. Where does it change? How about 5.5? Oh, it changes a little bit. 7.9. Doesn't really change from 5.5. 9.9. Oh, there it changes. Now, at any pH above this, you could just go 10, change it, 0.1. And you would see that this molecule is not going to get any more negatively charged given a higher pH. So if you're looking for a good resource, I think this is a fantastic resource. And it's easy to do. It gives you, you know, I mean, I'm not going to tell you what to do with your lives, but I think that this would be a good like business opportunity. You could, in the sense that you could become a tattoo artist who specializes exclusively in doing peptides. Um, and I mean, the thing is though, with like becoming a tattoo artist, I think, you do have to practice. And so that means you will have done a bad tattoo on someone at some point. And so you just have to find someone who's willing to do that. But I think that if your specialty is peptides, that's lots of straight lines. So that should be good. But of course, you know, people don't have like completely flat surfaces on themselves. So when you're doing that art, it might be like, well, it looked good from this angle. Now let's, huh. Anyway, that's a separate thing. So, um, is it? Is that a cat?
It's
Is
a
that a
dog.
dog? Okay, it's a dog. Oh, those are ears. Okay, you're the bottom cell on my whatchamacallit, my screens here. So I couldn't see. Is that a Frenchie?
Yeah.
Cool. Cool. That's fun. It's fun. Are you at a vet clinic?
No, I'm at work.
Okay. Okay. Well, welcome to class, puppy. Okay. So, um, that was big aside, but that's because I think that that is a very important part of preparation for your exam on Monday. Um, Being able to, identify your amino acids, how they're classified, um, what they look like at a different pH. If you like, that's lots of heavy lifting for Monday's exam. And people asked the other day, like, "Oh, I need to know all of them." Yeah, but you could I would look at it in a slightly positive way of like, I need to know all of them, and for all intents and purposes, that's most of what I need to know for Monday. If I were to like, if you can classify your amino acids, identify them by full name, single letter, three-letter codes, and see what they and select what they look like at different pHs. I feel like that's like 30 out of 40 questions right there for that content. Or let me translate that a different way. That's like 75% of the content or of the questions related to that content. Um, and I say that knowing full well that that's because this doesn't go away. Like that's such a big part of this class. And so if anyone's ever, shared any sort of like horror stories of biochemistry, like you got to know your amino acid structures. Yeah, you do. Because that's like being able to read and knowing the alphabet. Like you have to know it. So our kind of transition or a segue away from that, and I'll pause if anyone has any questions. Get a drink. Okay. Oh, and I'm drinking a big gulp, a super big gulp. This is Diet Coke, and I believe this has aspartame or aspartame, which aspartame is an ether of aspartic acid and glutamine. So those two amino acids, no, aspartic acid and phenylalanine. Those two amino acids make an artificial sweetener. Yes, Christian.
So you said to know how the amino acids are going to react differently in different pHs. So,
Let me just correct you on the word react, and how they will change. So how they will ionize. So it's not like any new covalent bonds are going to be formed or anything like that.
okay, is that just to help calculate PI?
But also, you'll that's one part of it. But also, you will have questions that are. I'll give you a picture of an amino acid, and I'll say this molecule, as it's displayed, is most likely in a solution of what pH? And then I'll say a pH of 1, pH of 4, pH of 10, pH of 14. And then you'll have to look at it and say, okay, this group is protonated, deprotonated, deprotonated. Based on those groups being deprotonated, this being protonated, then I think that this is in a solution with a pH of 4. Just as an example. Does that make
Okay,
sense?
yes. Thank
Great.
you.
Sure. Um, Okay, and then one last thing. I think what I'm going to do next week is keep Tuesday as an asynchronous class. And then Wednesday I'll jump on basically as like office hours, but I'll have that lecture recorded so that can be done asynchronously. So if you don't have any questions, don't worry about it. And then Thursday, so it's like Tuesday and Thursday will be asynchronous. Um, Wednesday will be like semi-synchronous, I guess. Synchronous for like office hours, more or less. And then Friday will be like this, where I'll go over like the high points of the exam and everything like that. Okay, cool. Well, here we are, protein structure. So there are a couple of different levels and organizations of protein structure. And their naming is pretty simple. It's primary, secondary, tertiary, quaternary. And you'll sometimes see this denoted like this: primary, secondary, tertiary, and quaternary. These are different levels of organization. Here we have a list of the sequence of amino acids going from the N termini to the C termini. So this right here, I'm going to go ahead and scribble this out. This would be an example of the primary structure of a protein. That primary structure, with all of these different amino acids, we're going to have different R groups. When it comes to naming or knowing your primary structure, we don't care about what those R groups are doing. We don't care about their protonation state. We don't care about the reactions that they can have or the interactions that they can have. Instead, we're just listing this out as a sequence. It's almost like um, I, I I find it helpful to say, okay, well, um, imagine that every amino acid is, you're a first grade teacher, and every amino acid is a person, is one of your students in your class. You get the class roster and you say, I'm going to put Joe first, Sally second, Anthony third, Daisy fourth. That's your primary sequence. You don't care that Joe and Daisy hate each other or that Sally and Steve punch each other every time they're next to each other. All that you're saying is from first to last, that's my sequence. That is all that the primary sequence is. Now, your secondary structure, depicted right here. Well, this is where things get a little bit hairy because here, what you're seeing is, okay, well, sure, this is great, but the way that I've constructed my line, it's not go like this is in an aqueous environment. This is not going to exist as a completely straight uniform line. Instead, what's going to happen is my students are going to kind of the line's going to curlicue a little bit. In which case, this is a structure. These are commonly known as local structures. So your secondary structure is referred to as having local structures. So this is where there's a little side conversation, and I came up with names of people, and now I've forgotten what those names were. So I'm gonna go Joe, Daisy, Sally, Dave, Anthony, and Rod. I picked nothing but names from the 1950s, I think. And of course, my own name that people call me. Even though my name is Joel, I regularly get Joe. So here, what we see for the formation of our secondary structure would be something where it's like, well, Joe and Sally, they're not right next to each other, but you know, maybe they're siblings, in which case Joe and Sally are going to kind of gravitate towards one another. And they're just going to be like, well, are we like, are we siblings where we're best friends and we hold hands? Not necessarily. But I know Joe, and Joe is sort of like I'm comfortable around Joe because I live with Joe. Joe's my sibling. So there's a little bit of a contorting. Now, in the structure of a protein, we see these local structures form, and here is one example. This is a helix. Now, the tertiary structure, this is where you have like personalities of the individual amino acids come out. And this is where, like, I have several kids, and you know, some of them like can't keep their hands off each other. Like the let's just say the third grader that I have is like, I'm gonna punch my first grade sibling. Why? Because because I'm going to do that. And that would be, let's say Joe is just like, when Joe sees Dave, Joe is like, I've just got to go push him. There's something instinctual in my person that I just have to go and push Dave. And then Dave is going to be like, well, as soon as I get pushed, you know what happens? I just start crying. And then Sally at the same time is like, I don't like seeing violence. And so I'm going to start crying as soon as I see Dave get pushed. And then Dave's going to start crying. And these are the individual. So for this case, that would be, and I hope everyone can follow my, the personalities are the R groups. So Joe would be a positive charge and Dave would be a negative charge. And so these groups, they might be attracted to one another. Now, the thing is, the way that a protein's going to fold, let's just go ahead and draw a polypeptide like this. This polypeptide might be amino acid 1, here's amino acid 350. Now, I always like to visualize a polypeptide or a protein as like a shoestring. What can you do with a shoestring or a noodle or anything like that? Well, it can loop back. So even though on a straight line, amino acid 1 is as far from amino acid 350 as amino acids in this polypeptide can be, because this exists in 3 dimensions, or actually just 2 dimensions for that matter, this thing can loop back and amino acid 1 and 350 can be right next to each other. So that's where we have this kind of tertiary structure, this higher level structure where it's not local structures. It's not local interactions. Instead, it's like comparing the full length of the polypeptide. These things are far away, but they can interact with one another. Okay, so 1 through 3, I want you to think about those as being, or the way that I kind of think about them is 1 is on the x-axis. That's your primary structure. Your secondary structure, it's a little bit more your x and your y-axis. So it's 2 dimensional. Then your tertiary, well, what's after our 2 dimension? It's dealing with our x, y, and our z plane. And so this is like a 3 dimensional depiction of a protein. So this is what this protein looks like in 3D space. I always like to use a piece of paper as a model to depict the 3D structure of a protein, and I can get some junk mail earlier today, so I'm going to use that. So this would be my primary structure. This would be like my tertiary, my secondary structure. How these overall interact would be something like this, where this has 3 dimensions to it. Now, whenever we get to our 4th level or our quaternary structure, this is where we're going into like a different level. This is, again, your 3D structure, but your 3D structure of multiple different proteins and how they fold together. So it's almost like you have 1 dimension, 2 dimension, 3 dimensions, and then you don't have a 4th dimension because it's not like suddenly the protein's going to smell or anything like that. But instead, you have a 4th dimension in that you're adding other proteins' 3D structures to what you're visualizing there. So this is an important point that everyone needs to keep in mind, is that a single polypeptide will have a primary, secondary, and tertiary structure. So it will have a sequence, it will have some local structures potentially, and then it will take a shape in 3D. A single polypeptide will not have a quaternary structure because it's only one subunit or one polypeptide folding by itself. Now, when you understand those different levels, it's also very important to understand the forces that stabilize those. Your primary structure is stabilized by nothing but covalent bonds. Specifically, I'm going to change this from covalent, I'm going to change it to peptide, because peptide bonds are the bonds that link every single amino acid to one another. Secondary structure is determined predominantly by backbone hydrogen bond interactions. This is where it's almost like that, yeah, there's 2 amino acids that are siblings, but you're not seeing any of their personality play out. Instead, it's just like they have something in common, and that would be they have a backbone And so that's what's going to stabilize your secondary structure. Your tertiary and quaternary structure, this is where your personalities are going to come into play. Every single amino acid is going to have a different property and a personality trait. So if we look at this figure below, this right here, your helical structure and your sheet, these are local structures. These are your secondary structures. These are not the R groups interacting. Instead, these are just how the backbones will interact with one another. Then if we look at hydrophobic interactions, disulfide bonds, metal ion coordination, hydrogen bonding from side chains, and electrostatic interactions, these are all tertiary and quaternary structures. Now, I love this figure right here because I think that this is a good way to practice and speculate, like, okay, what types of interactions are doing this? Or not what types of interactions, but what amino acids can bring these two things together. So here what we have for our hydrophobic interactions, if something is hydrophobic, it's water fearing. If something is water fearing and therefore hydrophobic, well, then chances are it's going to be a non-polar amino acid. So here we have an example of valine and isoleucine. Those are two non-polar residues that stabilize or that are brought about through hydrophobic interactions. Other alternatives from valine and isoleucine, you could have a leucine and a glycine, and alanine and a glycine. And if you're watching there, I changed an L to an A. So man, oh man, I was a genius when it came to bringing my report card home to my mom. I didn't make an L in that class. I made an A. Not really. L isn't a grade. And the one time I did try doing that, it was pretty apparent. So then I just got in trouble for two things. So non-polar residues, non-polar R groups are going to bring up about these hydrophobic interactions. Disulfide bonds. Well, that's a covalent bond between two amino acids. This is kind of unique because there's really only one amino acid that can do that. Does anyone remember what that amino acid is that can stabilize or that can form a disulfide bond? I'll open it for the chat. Or what two amino acids have sulfur, methionine, and cysteine? Which amino acid can form a disulfide bond? That's right, cysteine. So two cysteine residues. So that's the only amino acid that can form that. Okay, great. And Galileo, you're absolutely right. It's a cysteine. Cysteine is what forms from the disulfide bond formation. Great job. So then if we look at metal ion coordination, this is a little bit tricky because what this shows is a divalent cation, M2 plus. Well, obviously, if you look at the periodic table and you're looking for the single letter M, you're going to be looking for a while because M does not exist on the periodic table. However, that M is just representative of a metal. So magnesium, Mg2 plus, could go in that place, Ca2 plus. So a cation jumping in there. Well, what is a cation going to attract? Well, it's going to attract a negative charge. So what this interaction can be formed by is a pair of negatively charged residues. So two glutamic acids and two aspartic acids, or a glutamic acid to a cation and aspartic acid to that same cation. And then of our last two, we have side chain hydrogen bonding. Well, this is right here an example of a hydrogen bond side chain form. So this would be something like a serine and a aspartic acid. So this is one of the things, like, let me go ahead and when it comes to knowing your side chains, knowing your R groups, this is one of those sorts of questions where you're applying that information to say, okay, which amino acids are capable of this? Now, I erased all of that because what I want to have y'all do for just a second is look at these different groups. if we have metal ion coordination, we're going to need a negatively charged R group. What are our negatively charged R groups? Aspartic acid, glutamic acid. Okay, so D and E. Okay. Then if we talk about side chain hydrogen bonding, ooh, residues that can participate in side chain hydrogen bonding. Well, here we have an example of, well, that would be a carboxylic acid. Carboxylic acid is the R group found on an aspartic acid and glutamic acid. Then a hydroxide group. Well, there's a handful of groups that have a hydroxide. That would be like your serine or a threonine. So S, T. Are there other amino acids that can participate in hydrogen bonding? Yeah. Glutamine, asparagine, um, tyrosine. That's a Y. Um, so yeah, there's some other amino acids. Then if we look at this electrostatic interaction right here, we're talking about an amino group, an NH3, which that can be found on the N termini of a polypeptide. It also could be found on an arginine, a lysine, or a histidine. And then this carboxylic acid can be found on the C termini of a polypeptide or on D and E. Now, what I really want you to take away from this exercise that I've just shown you is D and E, D and E, aspartic acid and glutamic acid. Knowing those two amino acid R groups give you players that can participate in hydrogen bonding, electrostatic interactions, and metal ion coordination. So I mentioned yesterday, like, hey, where would I start with learning amino acid structures? I'm starting with those negatively charged residues because those negatively charged residues are going to be helpful in a number of different settings. Then after that, I'm going to go to my positively charged residues. And then after that, I'll go to the remainder of my polar amino acids. And then last but not least, my nonpolar residues. So when you look at something like this and you're thinking about those R groups and learning those R groups, it's, I think, helpful to think like, well, what could they participate in? That's going to be the way that I begin learning these. Okay. So um, we mentioned peptide bonds. Peptide bonds, those are the covalent bonds that form between amino acid, the N and the C termini of an amino acid or of amino acids. Peptide bonds are stable. They're very stable. Prolonged exposure to a strong acid or a strong base at an elevated temperature is required to hydrolyze them. So we're talking about 6 molar HCl at like 100 degrees Celsius for like an hour. Then you're going to break peptide bonds. So those covalent bonds are, as advertised, they're very strong. Now, the structure of a peptide bond. Here, what we have is one, two, three structures, three resonance structures, or three different displays of these molecules. Now, what we see over here on the far left-hand side is the one that you're going to see probably more than anything else. But those depictions in 2 and 3, those are also true. So the structural properties of the amide or peptide bond are very important to the overall structure of the protein. Peptide bond has 2 resonance structures, has partial double bond character, and therefore it's fairly rigid. So it's kind of in between being a single bond and a double bond. It's about 40% double bond, making it stronger than a single bond, but weaker than a 100% double bond. Now, this peptide bond is uncharged, but it is polar. Now, let's think about that. Uncharged. So it's never going to adopt, which is why we see figure 1 here. It's never going to adopt a positive or a negative charge here or here. But due to this resonance stabilization, we can have partial negative and partial positive charges. Now, that's significant because let's think back for a second and actually let's jump back in time here. Our secondary structure is determined predominantly by backbone hydrogen bonds. backbone hydrogen bonds. So we have groups right here that can participate in hydrogen bonding. What are the groups that can participate in hydrogen bonding? Or the atoms N, O, F, and H. So this oxygen right here, or this nitrogen right here, can help form a hydrogen bond. And that's going to lead to these local structures forming. Now, the structure of a peptide bond, as we know, it was first described by Linus Pauling in 1939. Linus Pauling was one of a few people who earned multiple Nobel Prizes. His Nobel Prize in the can't remember what it was for in the 30s, but then in the 50s or 60s, it was the Nobel Peace Prize. Um, he's someone who I forget how recently he passed away. He died in the early 90s. And I just mean that in contrast to like scientists that you learn about, von Leeuwenhoek and what's their names? Anyone who's in like, people who, elucidated the structure of a cell. They died in like 1806. I'm not saying that it doesn't matter, but it's always like, oh, I've heard of the 1990s. That's relevant to me. So, in addition to a peptide bond being fairly stable and strong, it forms a plane, the atoms of a peptide bond, the six atoms that are depicted here, these one, two, three, and four within this straight line, five and six, these atoms are all in a plane. Now, if you look down at the bottom here, this main chain, if you look at this kind of that green square, I always kind of visualize that as being like my hand. Then, so this would be my left hand, and then this one right here would be my right hand. So my hand is not going to, it can change, it can rotate, but we're not going to see something like this happen or that or anything like that. So the atoms on those six atoms are going to exist on this plane. That plane can rotate, but I'm not going to like bend anything on that plane. Does that make sense? Okay. So then the next group of six atoms, these can rotate relative one another, but the six atoms within each plane are largely not going to, like, they're going to exist on this plane different from this plane. So there's rotation, and that's how we basically get the overall structure of a protein. These rotations will take place, and this might be a favorable positioning compared to this or this. Now, if you are to visualize that, these kind of meeting points, basically where my two middle fingers are meeting together, that's where an amino acid R group is going to be found. And so I can have this rotation, and that R group might rotate based on movements of my two planes. Now, the twists can occur about either of the bonds linking the alpha carbon to the other atoms of the peptide backbone. The dihedral angles describe the conformation of the entire peptide backbone. There are two angles per peptide plane. Now, what I want you to know about are the bond angles that basically are stable and unstable. So there are a pair of them. Phi describes the rotation about the NC bond and involves those different atoms, CO, NC, CO. And in just a second, I'm going to show you the way that I think about this. Then our psi angle describes the rotation between our alpha carbon and our carboxy termini. Now, the way that I visualize this is I draw a polypeptide. I write out my polypeptide. I say N, C, C, N, C, C, N, C, C. This is helpful for me just to get a sense of, okay, what are the bonds that I care about? Now, my phi angle, I'm going to use this backbone and I'm going to say, oh, well, my phi angle is N to C. There, there, there. Then my next, so it goes just as it's almost like I say this enough and it triggers a memory for me. So I'll say NCC, 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 NCC. That's how I know to draw. That's my backbone for a protein. Then I'm going to say phi, psi, peptide, phi, psi, peptide, phi, psi, peptide. So the one that's unlabeled here that I'm now writing in blue is my peptide bond. So what I'm interested in learning about and what biochemists are interested in learning about are the rotations that these phi angles that I'm circling right here and the psi angles can rotate. So basically, the bond angle that causes my middle finger to rotate causes the entire plane to rotate. Does that make sense? This is complicated and this is abstract. So to visualize this, it's not a trivial effort, but use my left hand and I'm going to write, let's see. I had a Sharpie down here, but I don't anymore. So the middle of my middle finger. So NC. Then the tip of my middle finger is where you'd find the other C. So this can rotate. And whenever I move my middle finger, it's almost like I'm driving the rotation of my middle finger. What happens to the entire plane? It's going to rotate. So imagine that you grab my middle finger and you rotate it, you turn it. Okay, you can turn that. So you're turning that plane. Now, when you turn that plane, essentially what you're doing is you're causing my finger in this plane to rotate. Let's say I'm going to turn it this way. I'm going to call that positive 90 degrees. I'm going to rotate it back. That's back to 0. I'm going to rotate it the opposite direction. That's negative 90. Now, if you can't imagine, there's a certain angle measurement or there's a certain rotation that I can do where it's comfortable. And then there's a certain rotation that I can do where it's completely uncomfortable, maybe even impossible for me to do. That's essentially the pressure that these different angles are dependent on. Now, keep in mind that this is a rotation, this is a single rotation that I'm doing. But then everything that I do downstream, like if I rotate this plane 90 degrees, what do you think is going to happen to this plane? Well, it's probably going to gravitate to go in that same direction. So if it were to go in the opposite direction, just as my hands, like if I move my hands, okay, this is a 90-degree rotation, but then I move this one back, I can't move this more than negative 90. So these rotations are kind of dependent on one another. Now, all that to say, what I want you to know about is I want you to see a figure like this and be able to identify your phi, psi, and peptide bonds in a peptide backbone. So N to C is phi, C to C is psi, C to N is peptide. If you remember that, that's going to be very helpful. Now, this plot right here is known as a Ramachandran plot. This is named after someone whose last name was Ramachandran. As is always the case, when somebody makes a profound discovery, they're like, I was just thinking, guys, maybe you think we should call this like the Joule theorem? And then everyone's like, yeah, we kind of figured you're going to go there. Anyway, okay, great. We will go with the Ramachandran plot. So, Ramachandran plot, what this shows us is this shows us a relationship between phi and psi angles. Now, if you look at this plot, you wouldn't be fooling yourself if you look at it and you say, well, there's only I would say less than 25% of the entire thing is really shaded. Most of it's like unshaded, most of it's white space. The shaded regions show favorable angles. So if we're talking about a phi angle, A phi angle cannot be rotated positive 90 degrees because our phi angle is going to be on this x-axis. So positive 90. Can it be rotated negative 90? Yes, it can. So the phi angle can be rotated negative 90. And you know what? The phi angle can be negative 90 so long as the psi angle is maybe around negative 170 to 180, right, in this region. Then maybe, let's call it this region right here, where we're talking about, I don't know, maybe negative 20 to negative 70, and then some positive regions, and then some other positive regions. So what this is showing us is that combination of favorable angles that can be attained. So what this means is that if you don't see like, if you do not see bond angles where you're landing in a shaded region on a Ramachandran plot, that means that that bond angle pair cannot be formed and form a stable molecule. So some values are more likely than others. Unfavorable overlap precludes some of the combinations of phi and psi angles. Okay, so that's basically your primary structure. These NCC, NCC, phi, psi, peptide, phi, psi, peptide. If you can keep that pattern in your head, well, then when you're taking your exam with Proctorio, it's going to be like, uh-oh, someone was up to something because they kept saying phi, psi, peptide. And then I'll go back and I'll be like, that is suspicious activity. Totally. I don't know what's going on there. So now when we get into like organization of a polypeptide, we have secondary structure. There are three major secondary structures, or yeah, secondary structures, I think it's fair to say. You might hear these secondary structural elements. They are an alpha helix, a beta sheet, and a beta turn. Now, when I took this class as an undergrad, we basically talked about an alpha helix and a beta sheet. We didn't talk about a beta turn, in part because, well, I don't know that it was really well articulated at the time. So the driving force for the formation of a secondary structure is the formation of hydrogen bonds in the peptide backbone. These are our local structures. Wool was one thing that was studied back in the 1930s by William Astbury. He studied proteins, uh, and he noticed these kind of diffraction patterns. This, well, key word there is a pattern. He noticed when he was doing X-rays of fibrous proteins from wool that there would be this sequence, this pattern that was particularly unique. Now, he showed that there were drastic changes in the diffraction patterns of moist wool fibers compared to whenever they were all stretched out. The unstretched showed periodic repeat distances of 1.5 and 5.1 angstroms. Okay, remember those distances, those lengths. And if you're thinking about 1.5 versus 5.1 angstroms, I can't remember what an angstrom is. Think of it as smaller than a nanometer. The stretched wool showed periodic repeats of 3.5 and 7 angstroms. Asbury proposed that the unstretched protein molecules formed an alpha helix, which he referred to as the alpha form. Stretching caused the helix to uncoil, forming an extended state, which he referred to as the beta form. Asbury was also the first to propose that main chain hydrogen bonds had a role in stabilizing protein structures. So he was the first person to say that it's not just these crazy R groups doing all of this. Instead, it's like the backbone that has a role. Now, we'll move past this one. Yeah, I'm gonna go straight to here. Let's get to the meat of the matter. An alpha helix, the rise per residue. So basically, when you hear rise, think about that taking into consideration the X and Y displacement that every single amino acid has. Because when you look at an alpha helix, like we see right here, well, yeah, it has an X height to it as well as a Y dimension to it. So the the idea is that each amino acid occupies approximately 1.5 angstroms. The pitch or rise per turn is 5.4 angstroms. And then the residues per turn is about 3.6. So that's one. So if we jump back to this right here, think about this as what is the amount of space, or what is the height for this helix to make a complete loop. So if we were to imagine here's one part of a helix, this piece of paper goes on to make almost two complete loops. Does everyone see that? So to go from where my index finger is from my left hand to now where my index finger on my right hand is, I've completed one total loop. That's one complete turn. So from where my left index finger is to where my right index finger, that height, that distance is the 5.4 angstroms. Now, then the question is, well, how many amino acids are required to make that complete rotation? And that's where this number comes in, 3.6, because we take the height of the complete rotation, and then we say, well, each amino acid occupies 1.5 angstroms. So we have approximately 3.6 amino acids required to make one total rotation. Now, I'm going to pause for a second. This is an opportunity to say, wait, stop, what do you mean? Okay. So now this next detail, go.
So sorry. For the 1.5, so would that be the horizontal measurement of angstroms? Just to clarify.
That's a great question. It's really more of it's accounting for the X and Y. So that rise component of it, or that referring to it as a rise, would be, it's taking into consideration kind of from both our X displacement and our Y displacement. So from here to here, that's 1.5 angstroms.
So it's like the angular measurement across.
Yes. Yes.
Okay. Will it give it to you usually?
I'm happy that you asked that, because these two numbers right here, 1.5 and 5.4, those are great ideas for formal tattoos. Those, you need to know those two numbers.
Oh, okay.
Because, and I would say that's because lots of these other numbers end up being kind of average values. So if we've got about, if we have a, yeah, 5.4 divided by 1.5, we have approximately 4 amino acids. So 3.6, nearly 4 amino acids completing one total rotation. Now, this next point right here, on average, there are 10 residues per helix. Now, this statement right here, I know that always confuses and frustrates people, because they look at these last two bullet points, 3.6 angstroms per turn and 10 residues per helix, and they say, how can those both be true? Well, the way that they can both be true is take for a second and kind of draw out this helix. If this, I can't, okay, X to Y, excuse me, that's about 3.6 amino acids. Y to Z, that's about 3.6 amino acids. So if this from X to Z, there's a couple of things that are important about that. For starters, that is, well, 5.4, and then this is 5.4. So this is a total of, from X to Z, that's 10.8 angstroms. That's one important thing. The next thing that's important is this is 2 rotations. So this is about 7.2 amino acids. Now let's imagine that this helix continues on and we're at, what's the letter after Z? Oh yeah, exclamation mark. Well, here we have a third rotation. So from Z to exclamation mark, that's 5.4 angstroms. So from X all the way to exclamation mark, that is 16.2 angstroms. This is about from X all the way to exclamation mark, that is 3 rotations. Those 3 rotations would be approximately 10.8 amino acids to complete that. So that helix is less than, that helix has more than 10 amino acids. So that is a larger than average helix. So these 2 statements right here can absolutely be true. The average turn, the average number, or the average rotation has about 4 amino acids. The average helix is more than 1 rotation. That's one thing that I know people always struggle with. Are there helices that are longer than 10 amino acids? Yeah, there's some that are, 7 amino acids. That's 2 rotations, roughly. Okay, so when we think back to what we said about William Astbury, the distances that he came up with were about 1.5 angstroms and 5.1 angstroms. And those are pretty darn close to what we see with our alpha helices or alpha helix calculations here, where, well, one one turn is 5.4 angstroms, and each amino acid is 1.5 angstroms. Now, will I have questions on the exam about these numbers? Totally. And so one of the questions that I really like to ask related to this is, there's a membrane, and I can ask, or I like to ask this in a couple of different ways. A membrane that is 40 angstroms thick. How many amino acids is required for an alpha helix to span this region? Okay, so essentially, if you think about a membrane as like a wall or a barrier, this barrier is 40 angstroms thick. We have an alpha helix that's going to look like my curly Q here that spans that. The question is, how many amino acids, or what's the minimum number of amino acids that is required to span that? So then what you do to solve this sort of problem is you say, well, 40 angstroms thick, and I know that I have approximately 5.4 angstroms per 1 rotation. Then I can say 1 rotation is about 3.6 amino acids. Now you could consolidate this point and this point into one part of the dimensional analysis, but it never hurts to practice dimensional analysis. I don't think it does. So then the question is, or the question was, how many amino acids did we need? We've got 40 angstroms, that's the thickness of our membrane. 5.4 angstroms is the depth of 1 rotation. And then 1 rotation is completed when you have 3.6 amino acids. So then we look at this and we say, all right, calculator, what do you got for me? 40 divided by 3, or 40 divided by 5.4. We get 7.047 times 3.6. And this would require approximately 26.7 amino acids. You could also do this as 40 times 3.6 divided by 5.4. And you would, lo and behold, come up with approximately the same number. Okay. So this is, these are calculations that are dependent on that 1.5 angstroms and 5.4 angstroms, and really kind of feeling comfortable with this terminology. Now, hydrogen bonding between backbones. This is backbone hydrogen bonding. So we had to have the groups that are capable of that hydrogen bonding. You have to have the C termini with an oxygen and the N termini with a hydrogen. So these two residues, there's ultimately a pattern. The alpha helix is a right-handed helix or right-handed spiral. So if you've ever heard that as a right-handed or left-handed helix, what that has to do with is put your hand in front of you and your thumb is going to be going up the center of that helix. And the directionality of the polypeptide is going to be how your fingers fold in. So I'm looking at the palm of my right hand, and the helix is going to be spinning kind of upward, where my fingers are folding in towards my hand because my thumb is going up the center of the helix, my fingers fold in towards me. Alternatively, a left-hand helix, like DNA, if I remember, I think it's BDNA as a left-handed helix. My left hand, it's going to go the opposite direction. So it's a left-handed helix. Now, the groups that pair up these hydrogen bonds are your C termini and your N termini. There's going to be a pattern, and that pattern is I to the I plus 4 hydrogen bond. Now, whenever I see a figure like this down here, what I always like to do is I like to establish where I am, position myself and say, like, okay, it's kind of like when if you've ever been to a mall or a state park or something like that, and you find a map, on that map, you can look at it and be like, oh, neat, there's lots of stuff. But then there's a little arrow, and that arrow says, you are here. And whenever you see that you are here, it's almost like, okay, good, I'm comfortable. I know where I am. This, I want you to do the same thing. What we know when we talk about amino acids is we know our alpha carbon. Our alpha carbon has our R group. So that's the first thing that I find. I'm going to look at this figure right down below, and I'm going to say, aha, there's my alpha carbon. Here's an R group. Okay. And then, you know what? Just for the heck of it, I'm going to say it's my phi angle. Psi, peptide, phi, psi. And now it's just going to get too messy, so I'm going to stop doing that. But I'm going to look at my R groups. Here's a second R group. Here's a third R group, a fourth R group, fifth, sixth. Okay, I feel good about where I am. Now, my first carbonyl group, well, that carbonyl group is going to form a hydrogen bond. So I've got an oxygen. I'm looking now for a hydrogen. And I'm looking for a hydrogen that's either bound to a nitrogen or bound to an oxygen. And I see that whenever I see this is amino acid I. This is I plus 1, I plus 2, I plus 3, and last but not least, I plus 4. So my N termini of amino acid I plus 4 will form a hydrogen bond with my carbonyl on amino acid I. Now, that's one hydrogen bond. The cool thing about hydrogen bonding is that it's a network of hydrogen bonds. Water, a solution, is a network of hydrogen bonds. So we see this network of hydrogen bonds here exists because we have now our next amino acid, which I'm going to switch colors so I can do this again. This next amino acid, I'm going to refer to that now as I, because this has a carbonyl oxygen. And that will form a hydrogen bond with, you guessed it, amino acid I plus 4. This is all relative. So it's almost like you look at a frame and then you shift it over, and then you shift it over, you shift it over, and you shift it over. So that's what was I plus one for my first hydrogen bond becomes I for my second. So I plus two, I plus three, and I plus four. These hydrogen bonds are going to be parallel to the helical axis. And if we look back at this figure right here, this shows us one of our hydrogen bonds right there. And that is parallel, that is alongside my helix going straight up. My hydrogen bond is right here next to it, it's adjacent to it. The last four residues at either end of the helix participate in only one hydrogen bond. What that means is that if this right here, if this hydrogen bond is the last one in my helix, that means that this group right here is not going to hydrogen bond, because where it's also, it's in another hydrogen bond upstream. Okay, so ultimately we're going to get a model that looks a little bit like this. We have those hydrogen bonds depicted here. And then kind of, this is, I like these figures, but it's kind of tough because you've got them in the foreground and the background. Now, one of the other things that I want to bring up to you is, have we talked in our discussion of secondary structures, have we talked about R groups other than identifying R groups? Have we said, oh, don't forget if this is an arginine or a histidine? No, we haven't, because those do not dictate, or those do not stabilize secondary structure. It's hydrogen bonding, backbone hydrogen bonding that stabilizes secondary structure. Now, as a little bit of an exercise, there's something known as a helical wheel. And this shows basically the amino acids and where they are on an XY axis and how you can visualize them. So if we look at amino acid number one, I always kind of think about that as like the bottom of the beanstalk. Then amino acid four is not directly on top of amino acid one, but it's a little bit staggered from it. And so what this shows, this helical wheel basically shows the amino acids that are on top of one another and where they are relatively to one another. So if we think about the distance from amino acid 1 and 4, that's about 5.4 angstroms. Amino acid 1 and 8, well, that's about 10.8 angstroms, because it's basically two rotations. Now, if I were to ask you a question like, which amino acid is most directly on top of one, is it 4, 5, or 8? The answer would be 8. Because 8 is, although it's a distance away from it, it's more close to obscuring it. Now, that's not the sort of question that I like to ask, because it requires you to kind of recall the helical wheel, but I think that it is important to visualize and to like have a sense of where these amino acids are. And I think you can get that sense from thinking about, well, is it 4 amino acids that make a rotation? No, it's 3.6, which is why we have, here's 1, 2, 3, and then for one complete rotation, it's right here. It's about 0.6 between 4 and 5. So it's about 3.6 amino acids that makes that distance. Now, an alpha helix possesses a dipole moment because each peptide has a dipole. The N termini has a partial positive charge. The C termini has a partial negative charge. An alpha helix, this is one of the sort of questions that I gave you a little bit ago. An alpha helix has 15 amino acid residues. Calculate how many angstroms the alpha helix would cover. So this would be 15 amino acids, 3.6 residues per turn. It's about 4.2 turns. 4.2 turns. Each turn is 5.4 angstroms. So we're talking about something that's 22.7 angstroms tall. So if you were to do the calculation slightly differently, you'd see that your math would vary ever so slightly. Now, whenever I've given questions that ask about these sorts of numbers, just a little bit of a spoiler for you. I am not going to give, well, A or B. Select the right one, because this is two different things to arrive at basically the same answer. Instead, it's going to be like A, 122.5, or B, 22.7. And then it's like, well, if you got 122.5, you went grossly wrong on your calculation. A 40 angstrom, oh, dang. It's like the exact same question that I gave y'all earlier. A 40 angstrom wide membrane. How many residues are required? Let's see if we get it right. 7.4 turns. We did it a little different, but we got 26.7. Good. There we go. Okay, cool. And I think that for the purposes of the amount of content, I'm going to go ahead and stop right here. So I'm stopping before we get to beta sheets. I'll leave that as like we're separating these two things from one another. We'll talk about beta sheets and beta turns.